So here's the example which will make us clearer about the meaning of degree of freedom. If you look at the system has two masses with two displacements shown here, x1 and x2, x1 and x2, with the force applied F. So to understand the meaning of degree of freedom, why it's more than 1 degree of freedom, if let us say I take M1, consider M1, hold. If we hold M1 and try to move M2, you will find that it can move. That means there will be a result of displacement on M2. Similarly, if I hold M2 and move M1 or apply force to M1, you are going to find that it's going to displace. I mean, there is displacements. That means in this system, it's going to result in two displacements. So now we agree that the system is 2 degrees of freedom. Let us look at the example and check what exactly we need to calculate here. In this example, he asked us to calculate x2 over f. As I mentioned, we have one input with two outputs. This is output number 1, this is output number 2. But he wants to get the output number 2 divided by the input. That's the system, or that's how am I going to consider the system. So he asked us to calculate x2 over f, x2 over f. Before we start in developing the transfer function, let us get clearer about the system. So in this system, if a force applied here at this position, M1 will move. As you see, there will be x1, which the movement or the displacement is due to the force. So this is, we agree on it. We have no problem with that. But the displacement will be transferred through FV3 or K2 will be transferred to the other side. And you will find that due to the force applied, there will be a force or a displacement on M2. If you catch this one, things will be very clear. Again, I apply force to M1, but the force will be transmitted to M2 through FV3 and K2. Now, similarly, if I apply force to M2, it's going to make a movement on M2 and it's going to transfer, or the displacement will be transferred to M1. Hopefully we are clear about this point. Why I'm describing it this way? Because when I want to develop the equation, I will develop the equation of M1 due to two effects. One effect, it's due to the force applied on M1 and due to the force coming from M2. So that's how I'm going to look at it. So that's what we will see in the next slide. Okay, so I'm explaining the system here to get you clear about this point. When I want to discuss or develop the equation, I will consider, for example, M1. The equation of M1 will affect or will be described by the element connected direct to M1 and the elements coming from the displacement of M2. Let us see it in the next slide. So here, what I mentioned, hopefully it's going to be clearer. When I want to consider M1, we are going to split M1 or the effects on M1 to two parts. One due to the motion of M1. Assume that M2 is hold. That's what we mean by M1. I assume that M2 is hold, and let us think of M1. What am I going to get? I'm going to get force with M1, with K1, FV3, K2, and FV1. These are the elements or the forces applied to the mass M1. So when I want to draw the free body diagram, we are going to put the force on one direction and the other forces in opposite direction. I hope now things are clearer. So now if I go to the other part, it's due to the motion of M2. That means when I want to evaluate the effect on M1, this is one part which done. The other part, it's coming from M2. So when I want to discuss it, I'm going to check what are the elements or the forces coming from M2. They are going to be seen through FV3 and K2. So those elements are going to be acting as a forces opposite to M1. So we are going to put them here. They are going to go on opposite direction with M1. Okay, now if I want to develop the equation, we are going to apply the superposition. So these elements all will be added together to get the equation of M1. Let us see it in the next slide. So here is the superposition. To apply the superposition, I will get both from M1 its own effects and the effects coming from M2. When we add them, we are going to find the forces are K1 and K2, FV1 and FV2, M1. These elements all are going on certain direction, opposite to the force applied. With the force applied and the effects coming from the other mass going on other direction. So when I want to translate it to mathematical expression, it's going to look like here. ms squared plus fv1 fv3s plus k1 and k2 all x1 of s minus, notice here, minus, because they are opposite direction, fv3 and k2 all equal to f. As if you look mathematically, you will find these elements all in opposite direction. But since F1 on the other side of the equation, that's why it's positive. But the force F and these forces are going to opposite direction as compared to these elements. Similarly, we are going to do for M2. Due to M2 and due to the forces transmitting from M1, we will apply superposition, and that's the equation which we are going to get. So we are going to use or solve the two equations. We apply the math here. The two equations 1 and 2 will be solved and rearranged to get x2 over f, and finally it's equal to this value, where delta is, you know, Cramer's rule, as delta is the coefficient of the quantity x1 and x2, and they are placed here. Now, here I'm going to discuss an easier way in dealing with the previous system. Much easier way. We don't need to go to those steps all. We can direct develop the equation without going to that detail. How am I going to do it? First of all, I know that the system is 2 degrees of freedom. If 2 degrees of freedom means the system will be described by two equations. And the displacements are going to be x1 and x2. So we are going to write the equations as you see here. And that's what we found in the previous example. We have here, this is equation number 1 to M1, for example, and this is to M2. At M1, we are going to get bracket multiplied into x1 of s, where inside the bracket, we are going to get all the forces or impedances, we call them impedances, linked to M1. All the impedances linked to M1. We call it, we give them the sign positive. Minus bracket x2, where we are going to get here in this bracket all the impedances linking x1 to x2. Notice the sign is negative. All equal to the sum of the forces applied to M1 or to x1. Similarly, we are going to put it here. We will put bracket x1, but here it's negative. Why I am putting negative? Remember, we are dealing with the second equation. So if I am dealing with the second equation, means the second item will be positive. I mean, x2 will be positive, or the coefficient of x2 will be positive. So here minus the x1 plus bracket into x2. Why I am writing it this way? Because I want you to know that when the link between M2 and X2, or M2 and X1, the link between them, their total will be placed here, total impedances. Here we are going to get the total impedances connected to X2. Total impedances connected to X2 equal to the sum of forces applied to that point. Let me describe this one on the previous example. I will put this idea on the previous example to see whether we will get the same result or not. So as I mentioned, it's the same example as before. I just want to describe the meaning of the previous formulas written. When I look at the system is 2 degrees of freedom. If it's 2 degrees of freedom, it will result on x1 and x2. In this case, I can write the equation like this. Bracket x1 of s minus bracket x2 of s equal to total f. Bracket which having the total f. What to write in the first item, first element here? Notice that I am doing the equation at M1 or equation number 1. Equation number 1 will result on x1. That means the quantities here will be positive and we are going to get all the impedances linked to x1 or caused x1. So what are they? They are M1 S square, we put it in Laplace, plus what elements, what other elements? We are having FV3 and FV1. FV3 and FV1. FV3 plus FV1, they are S plus what else? We have K1 and K2. Notice that all these elements are connected direct to M1. So here K1 plus K2. I hope you can see it nicely. Now finish. After I finish this part, I'm going to go to this bracket. What to put in this bracket? Remember that I am at M1, so I'm going to get the link between X1 and X2. The link between X1 and X2. What is the link between X1 and X2? We have FV3 and K2. So I'm going to put here FV3S plus K2 equal to the total forces applied. What are the total forces applied? We have only Fs. Finish. That's how we can get the equation. Okay, let me proceed to the next one. In the next one, we are going to get the equation on M2. How to get the equation on M2? We are going to write it as before exactly. Here x1, I am going to put here minus something into x1. So I have to put them in the same order. X1 here, X2 here. Then here X1, here X2. That's why I start with minus. Why minus? Because I'm evaluating for M2. And we will start by the link between M2 and M1. So I'm going to start with the link between X2 and X1. I'm going to show it after a while. Plus bracket X2 of S equal to the total forces applied. Let us see here. So what to put in X1? Here, coefficient of X1. Coefficient of X1. But keep in your mind, I'm calculating for X2 right now. It's M2. So what to write? I'm going to write the link between X1 and X2. So this link is same as before. So it's going to be FV3S plus K3. Now this is the elements linking X1 to X2. Here what I'm going to put here? What am I going to put here? I'm going to put here the impedances affecting X2 direct. What are they? They are M1, K3, FV3, and FV2 with K2, sorry, with FV2. So let us arrange them and let us put them. You are going to find that what to put here is M. Let me change the color. M2 S square plus FV3 plus FV2 FV3 plus FV2 all S plus, we didn't finish here, plus let me write it somewhere else. I will write it here. plus K3 plus K3 plus K2. So this bracket is going to be placed here in this location. I hope you catch what I mean. That's for x multiplied into x2, all equal to the total forces applied. Do we have any force applied direct to this location? No. That means here it's equal to 0. So if you can compare these two equations with the equations developed earlier, you will find they are the same. So we don't need to go to the detail discussed earlier. We can direct apply the equations without calculating them in that detail. I mean in superposition. We are going to develop the equation considering the equation shown in the previous slide. Here in this system, in this example, just want to teach us what is the meaning of degree of freedom again. What is the number of degree of freedom? And he asked us to generate the equation. We don't need to develop transfer function. Only he wants us to know the degree of freedom, which will result in writing the right number of equation. So when I look at the system shown clearly that it's 3 degree of freedom. How do I know this? Because if, let us say, I hold M1, and try to move M3, it's going to move. The same thing, if I hold, and M2 will move. Same way, if I hold M3 and try to move M1 and M2, they are going to move. You see, here is the second motion. Then the same thing, if I try to hold M1, M2, if I hold M2 and try to move M3 and M1, they are going to move. That means there are 3 motions here. There will be, by the end of the day, 3 different displacements. That's why we are going to call the system a 3 degree of freedom. Now, how am I going to develop the equation? Before I start writing the equation, I will apply the method mentioned earlier in the previous few slides. So I'm going to say here that since I am having a 3 degree of freedom, my equations going to look like this. In equation number 1, it's bracket x1 of s minus bracket x2 of s minus bracket x3 of s equal to the forces. Now, this is equation number 1. Equation number 2, I have to erase this to write equation number 2. Equation number 2 going to be here, minus bracket x1 of s plus bracket x2 of s minus bracket x3 of s equal to the total forces. This is equation number 2. Keep in your mind, these brackets need to be filled. These brackets need to be filled. But if you can catch this idea, after that, writing the equation will be something extremely simple. If you follow my technique, which I'm teaching you here, you will find that developing the equation will be something extremely simple. Now, if you want to think of equation number 3, let me erase this one first. Equation number 3 will be, equation number 3, you see, before I write it, I know that it's the causing displacement number 3. That means displacement number 3, which x3 having a positive coefficient, and the other coefficient will be negative. That's how I keep it in my mind. So I can write the equation as minus a bracket x1 of s minus bracket x2 of s plus bracket x3 of s equal to the total forces applied, if any. So if I apply the method here, if I look at this method, the equations I write, and compare them with the equation here, you will find, see here, this is a bracket because I am at 1. That means motion 1. This bracket, x1. Then bracket, he's not showing as a bracket, x2. Then bracket, x3 equal to the total forces applied. Now, what to put in the first bracket? We are going to put the total impedances linked directly to M1. What are they? If you notice here, this is M1. This is the first impedance, second impedance, third impedance, fourth impedance, and fifth impedance. They are connected direct to X1, and they are written here in Laplace format. Similarly, for the second one, you will find the link between X1 and X2, between X1 and X2. What is the link between X1 and X2? Notice here, this is X1. Here, this is X2. What is the link between them? Only K2. Only K2. That's why we will find K2 here. Now let us proceed. How about this element, this bracket? In this bracket, you will find the link between X1 and X3. X1 and X3. So let us look at the link between X1 and X3. This is X1. Here is X3. The link between them is only FV3. So we put it here, FV3. So that's how we are developing the first equation. They are equal to 0 because there is no force applied direct to this mass or to this displacement. That's why it's equal to 0. Apply the same idea on the second equation. Let us see how. Let us see how am I going to apply the same idea to the second equation. Okay, when I think of the second equation, I said earlier it's minus a bracket into X1 plus bracket X2 minus bracket X3 equal to the total F. Why this is minus, this is plus here, and this is the third one is minus? As I said, if I'm calculating for X2, the equation for X2, its coefficient will be positive. The other coefficients will be negative, which is the link between X2 and the others. What to put here in the first element? It's the link between 1 and 2. What to put here? It's the impedances on M2. The impedances connected direct to X2 or M2, because X2 is shown on M2. So they are the impedances on X2. What to write here? It's between X2 and X3. So after that, we are going to go to the other side of the equation. What to write here is the total forces applied. Where is X2? Here is X2. Is there a force applied to X2 direct? Yes, it's F. That's why here you put F. Similarly, you are going to get equation number 3. So that's how we can develop the equation without writing them in superposition, as I mentioned earlier. So once you see the system, the first thing to do is decide to the degree of freedom. So the number of equation will be known. After you know the number of equation, you can write the bracket and fill them. You are going to get the equation done without problem. Another example on translational mechanical system. In this example, he's asking us to find the transfer function x2 over f. Before we start doing anything, let us describe the system. The system is kind of box or mass M2 located on a floor. That means there is a friction between the mass and the floor at this location. Inside this mass, inside the box, there is another mass M1. This is M1, where M1 is having a friction between itself and M2 here, which another damping effect, and similarly it's having another friction in the bottom side. There is a link between M1 and M2 beside the friction F1 and F2. There are two links, which K, which connecting the mass 1 to mass 2, M1 to M2, and another damper which connecting M1 to M2. So that's how we can describe the system. The first thing I'm going to think of here when I see this kind of a question, what is the degree of freedom? To know the degree of freedom, we are having two masses here, M1 and M2. If I hold M1, hold it, and apply force to M2, you will find that M2 is moving. That means there is displacement on M2. Similarly, if I hold M2, and try to move M1, I will find that M1 can move, means there is displacement. That means there is another displacement called X2. So if I have two displacements, that means the system is 2 degrees of freedom. So we need two equations to describe it. Let us see this in the next slide. So I am putting the system here to help us to get the two equations, because we said it's 2 degrees of freedom means two equations are required. If I follow the same style as I discussed previously, I will find the system is 2 degrees of freedom with two displacements. One of them is x1 and x2. So when I want to do the equations, we have to keep in our mind that the equations are going to be bracket x1 minus bracket x2 equal to force, and minus bracket x1 plus bracket x2 equal to the total forces applied on the second part. He's applying the same idea here. Let us see how. So first of all, what to put in the first bracket? We are going to put the total impedances affecting x1. So what are the total impedances affecting x1? They are this friction, because they are linked directly to M1. The mass M1 with this spring and this damper. They are the elements the impedances connected direct to M1. So look how he put them: s square, that's the mass, plus 3s because it's 1, 2, and 3. Each of them is having the constant of 1, that's why it's a 3s, and the spring of 1, that's why it's 1. That's the impedances linked direct to x1. Let us go to the impedances connected here in this bracket. We are going to put the impedances connecting x1 to x2. What is connecting x1 to x2? So if you look at it carefully, you will find between x1 and x2, let me just erase this, between x1 and x2, there are one impedance here which FV1, one impedance here which FV2, that's the friction or the damping effect, another damping effect here, and another spring. These are the elements linking x1 to x2. So we will put them here to find that we are having 1, 2, 3, so that means the 3s plus 1 plus 1. That's how we can get the total impedances between 1 and 2. Let us proceed. To proceed, I need to say they are equal to the forces. Are there any forces applied on x1? Look here. The force is applied here to M1, where x1 is. That means we have F1 connected. That means the equation is equal to F1. So that's how we can catch the first equation. Let us go to the second equation now. We are going to get the second equation by the same way. Remember, I gave you the equations, the empty equation. Let me call it empty equation. I'll put the empty equation again. Empty equation here means minus bracket x1 plus bracket x2 equal to total F, if any. So what to put here? Since I'm now writing the equation of x2, when I'm writing the equation of x2, that means whatever x1 here will be negative. And we are going to put the link between x1 and x2. That's why here I'm going to put the link between x1 and x2. What is the link between x1 and x2? It's the same thing as before, because it's the same arrangement. So it's the same elements as before. So it's equal to, here it was a 3s plus 1, here it's a 3s plus 1, but this time it's minus. Again, why minus? Because we are getting to the link, to the forces coming from the other motion. Now, we will go now to the second part. Second part, I mean here, where we are going to calculate this bracket. What to put in this bracket? We are going to put the total impedances linked direct to x2. Total impedances linked direct to x2. We are going to put them here. Let us figure out what are those impedances. The impedances linked direct to x2 are, here we are having friction, FV1, and another friction, FV2, with this because they are linked, okay, with this spring, with this damper, with this damping effect as well. So these are the elements connected direct to X2. So we are going to put them here as I said just now. So they are S square, because yeah, of course, I forget to mention also M also linked to the same point. That's why here we are finding S square plus 4S, because there are 4 dampers, each of them having the constant of 1, plus 1, they are X2, equal to the total forces. Is there any force applied to this mass? No, that means we are going to put 0. Finish. Once we put the equation, the remaining will be simple. We don't need to discuss it even. Once I put the equation, I will solve this equation for the value I want. What do I mean by the value I want? He wants to evaluate X2 over X1. In the question, he said, find the transfer function X2 over, sorry, not X1, over F. X2 over F. So in this case, I will evaluate X2 out of these two equations by using a Cramer's rule. So to evaluate X1, if you notice here, we are replacing the column of X2 to evaluate X2. To evaluate X2, we are replacing the column of X2 by these elements, the other side of the equation. And here we are going to put the coefficient of X1, and here the coefficient of X1, here the coefficient of X2, a Cramer's rule. I hope you didn't forget the application of a Cramer's rule. We solve this, and we are going to find that the equation is going to look like this. We simplify this equation, and finally we are going to get the transfer function as you see here. When I simplify it, I will make it such that X2 over F. And this is finally the transfer function with the input of F and the output of X2. That's all regarding to the translational mechanical system model. I hope it's clear to you. I wish you all the best. Thank you.